And I want to thank the department for having me here and making this visit work out. So today I'm going to talk about some work that we've been working on at Princeton. This is a project that started about 5 or 6 years ago, and really what we're trying to do is we're trying to study light-matter interactions at the single particle level. And so we're going to make devices. These devices are called semiconductor double quantum dots, and you can think of them as designer molecules. It's a experimentally tunable double well system that we can put a single electron in. And I'm mainly going to talk about non-equilibrium physics today, where we're going to take this device and we're going to hook it up to a battery and force electrons to sequentially tunnel through these single electron energy levels. And I want to talk about this tunneling process and what happens. And what we've learned through these experiments is that we can actually make pretty nice microwave frequency photo emitters using these semiconductor double quantum dots. When we place them inside of cavities, there's a large electric dipole coupling between this system and the electromagnetic field of the cavity. We can see photon emission from the system. We can also make a microwave frequency laser, a maser, that's driven by single electron tunneling events. And so I wanted to give you a sense of the experiments that we can do with the system and the amount of control that we have with this experimental platform. I have a really great research team that's pushed this field forward, and I want to acknowledge Carl Peterson, who kind of kicked this off back in 2012, and more recently, a graduate student, Yin-Yu Liu, has really led the charge on this project, and you'll see from the paper, she's had a leading role in the success of these experiments. Okay, so overall, the field of physics I want to talk about is cavity quantum electrodynamics, and generally, in the context of this field, you can think of having two mirrors that make a high quality factor cavity that we can trap light in between. And what we want to do is couple a two-level system to this cavity field. And this interaction is described by the famous Jaynes-Cummings Hamiltonian, which basically says, all right, I have a harmonic oscillator type of system here where I can trap photons in the cavity. They have energy h bar omega, and we have n photons in the cavity, so some photon energy. We have a two-level atom, which is just described by the simple sigma z term in the Hamiltonian. And then the interesting part is this interaction term, which basically says that if there's a coupling between this two-level system in the cavity, you can have a coherent flip-flop kind of interaction where the excitation gets passed from the atom to the cavity and back and forth at the vacuum Rabi frequency, which is described by this parameter g. And so there's a lot of interesting physics that goes on when this coupling rate g, the vacuum Rabi frequency, is greater than the loss rates. In conventional kind of atomic physics implementations of these experiments, you have to worry about the rate at which photons leak out of the cavity. That's described by this loss rate kappa. Atomic system will have some intrinsic decoherence or relaxation rate gamma, and the strong coupling regime is when this coherent coupling rate exceeds all the sort of bad loss rates in your system. Okay, I think what's exciting about this field is a little over 10 years ago, it was shown that in condensed matter systems, you could explore very much the same physics, but using solid state devices that are fabricated on chip. Right? And so instead of having an atom transit through a cavity for a finite period of time in an atomic physics system, we can now make devices where you have a tunable condensed matter two-level atom that's coupled to a cavity field, and you can really probe exactly the same physics as in these atomic systems. And so I'm going to talk about this work in a non-equilibrium setting where we're going to sort of drive the system out of equilibrium by hooking it up to a battery and also applying other external drives to the system.
Up to what time scale will it remain coherent?
So it depends on how good the cavity is, and that rate is described by kappa. So generally, at least in the experiments in our group, the cavity decay rate might be about 1 megahertz, right? And then this interaction frequency g can be anywhere between a few megahertz up to several hundred megahertz in some superconducting experiments, probably, sort of typical range. Decoherence rates vary widely, depending on the system. And so for charged qubits, they can be very fast, like gigahertz frequencies. There are these transmon-based qubits where you sort of flatten out the bands and you can have longer coherence rate. And so that's kind of the trick, is finding a system where you actually have control over the parameters in your Hamiltonian, but you can get into this interesting, coherent interaction regime. But that kind of gives you a rough idea. There's, in most systems, you can have interaction rates that are a factor of 10 or so better than any of the loss rates in the system. Okay? And feel free to interrupt if there are questions. Just raise your hand and stop me, and we can dig into more detail. Okay? Good. So I want to describe 2 experiments involving circuit quantum electrodynamics with quantum dots. The first experiment, I'm going to spend most of my time talking about this. I'm going to show you how we can make a micromaser that's driven by a single electron tunneling event. So we're going to take a device, it's called a semiconductor double quantum dot, and we'll place it in between 2 mirrors, a microwave frequency cavity, and look at what happens when we drive a current through the system. And I'll show you that if we have a gain in the system that exceeds all the loss rates, we can achieve a sort of above threshold maser action. We see self-sustained oscillations, microwave frequency photoemission from this device. In the last part of the talk, if there's time, I want to talk about another experiment, probes non-equilibrium physics, but we call this a Sisyphus light source. And Sisyphus is a character in Greek mythology, and he was punished for chronic deceitfulness. He lied a lot. And the story is that his punishment was to push a boulder uphill only to have it roll back down, and he'd push it back up and roll back down. That was his punishment, to do that over and over again. And so the idea of this experiment is to make a Sisyphus experiment with 1 electron. And the idea is that we want to take 1 electron and apply a non-adiabatic perturbation to the system that kicks that electron up into the excited state, only decay to the ground state by emitting a photon, and repeat that process over and over again to try to generate single photons by pumping the system non-adiabatically. So I'll talk about 2 experiments, one where we're driving charge transport by hooking up to a battery, and another, I'd say, more controlled or quantum coherent experiment where we're actually modulating the quantum dot energy levels in a time-dependent fashion. Okay? Good, so let's start off with some basics. I want to talk about the overall physics of our devices and how they work. Let's just review quickly how lasers work. If we want to make a laser or a maser, there are basically 3 key elements that we need to put together. We need some kind of gain medium that when light passes through is amplified. And generally, you like to have the light pass through the gain medium multiple times, many round-trip transits, so that you have a lot of amplification. And the way that's done is by placing the system, the gain medium, between 2 mirrors, so that gives you optical feedback. The third thing that we need is some kind of energy supply. And physically, what this energy supply does is it generates the population inversion that's needed for stimulated emission. And here's a graphical picture of a stimulated emission process. You can imagine that we have a simple 2-level atom with a ground state energy and excited state energy. These are separated by some energy, h bar omega. And if we have an incoming photon that has an energy that's close to this transition energy, and we have a way of preparing the system, the excited state, we can have a so-called stimulated emission process where this photon comes in, it interacts with the 2-level atom, and we get 2 photons out. And so the energy supply is what's going to give us this population inversion to kind of prepare the system in the excited state. What I found really surprising about this field is that a lot of things will laze and maze, and there's a long history of this, several kind of Nobel Prize winners talking about this, but here's one quotation that I particularly like. This is from Arthur Shallow, claimed that anything will laze if you hit it hard enough. And so just to get things warmed up, I want to give you a few examples of this. Here's a simple one, a diode laser, like the diode laser I have in my hand. This is generally made out of a semiconductor heterostructure. The gain medium is just a PIN junction. It's basically a sort of diode type structure. And the way the cavity is made is just by cleaving the ends of the crystal. So you take the semiconductor, you cleave it, you have 2 pretty flat surfaces that light bounces back and forth between. The energy supply is a battery. Here's a more exotic one that many of you probably haven't heard of. This beast is called a gas dynamic laser. And a gas dynamic laser is actually a combustion-based laser. It runs off of gasoline. And here's the way it works. There's a combustion chamber here that the air-fuel mixture goes in. This is ignited very much in the same way as, say, a 4-cycle engine. And that gas rapidly expands and is forced through some very small nozzles. When the gas goes through the nozzles and expands, it cools at about a rate of 1,000,000 degrees per second. It's a very non-equilibrium process. And this rapid expansion gives the population inversion that's actually needed for the stimulated emission. And so this particular system can be used to make very high power, hundreds of kilowatt kind of lasers. It's called a gas dynamic laser. And then another interesting story, it's after lunch now, but Arthur Shallow and Hansch also investigated whether or not you could make an edible laser. And so this was a slow day in the laboratory where they went to the store and bought 10 different flavors of Jell-O. Does everyone know what Jell-O is? It's not a very nutritious food, but it's kind of common in the United States. And they tried to make Jell-O Lays, and they showed that under certain conditions you could actually get stimulated emission, from certain types of gelatin. So there's some truth in the statement that anything will laze if you hit it hard enough. And I want to tell you a story about this quantum dot micromaser. It's at the different end of the spectrum compared to these three examples, right? It's going to be a device that's based on single electron transport. It's not hundreds of kilowatts, it's a picowatt or smaller power scale. But what's interesting is it's really driven by single electron tunneling events through discrete quantum states in a semiconductor system. Okay? And so here are the key components of our device. The gain medium that we're going to work with is a semiconductor double quantum dot. I'm going to spend quite a bit of time just talking about the physics of what that device looks like. We place it inside of a high quality factor microwave resonator. That's the cavity that is going to trap, in our case, microwave frequency photons. And then the way that we pump the system into the excited state to generate the population inversion is we can simply hook it up to a battery, which is going to repump the excited state in the stubble well system. Okay. So let me dig in a little bit, just a background of our field of quantum dots. Now, what is a quantum dot? Basically, a quantum dot is any system, right, that will give us three-dimensional electronic confinement, right? And there are a number of ways to do this. One way to do this is to try to take a single molecule and trap it between source and drain electrodes. You can take a metallic nanoparticle that's chemically synthesized and trap electrons on that. In the semiconducting realm, there are two ways to do it. You can take a semiconductor and etch it to make a smaller kind of quantum dot structure that you trap charges in. Or instead of etching, I'd say the preferred way to make a quantum dot now using semiconductors is to fabricate on the semiconductor local depletion gates, like in this example shown here. And these depletion gates can be used to corral a single charge in the nanostructure and basically make a quantum dot. But we want to put a cage around an electron. And these are the ways this is done practically in the laboratory. Quantum dots are many times called artificial atoms. Here are a few reasons why. Right, for an atom, we have a Coulomb interaction that bounds the electron to the nucleus. In our quantum dot devices, we will have a lithographically defined confinement potential that's going to trap a charge or some certain number of charges in a region of space. If you take a gas cell, for example, and shine light through it, you'll see a discrete absorption or emission spectrum. We can take quantum dot devices and hook them up to electrodes and actually probe the transport properties, the current or the conductance relations, and we can resolve discrete energy levels in a quantum dot, just like you would do through some kind of spectroscopy in an atomic system, okay? Can also take atoms and couple them together to make molecules. Water is an example. And in quantum dot devices, you don't need to work with one quantum dot. You can put two quantum dots close together, and the wave functions will hybridize, and you can have something that's called a double quantum dot. So you can kind of make man-made molecules, so to say, of these quantum dot systems. What are the differences? The first thing is size. Instead of having angstrom length scales, we're working with lithographically fabricated devices that generally have length scales that are on the order of 10 to 100 nanometers, so much bigger. And due to the larger size scale, the particle and the box energy scales are a lot smaller. So the transition energies that we deal with in our devices, a lot like superconducting systems, are in the 10 to 100 micro electron volt range. And that forces us to do our experiments at low temperature, so we can basically freeze everything into the ground state. In terms of condensed matter physics, I think it's a much more interesting system in some ways. We have an extended wave function. It encompasses about 1 million lattice nuclei, and this leads to complex hyperfine interaction. And also there's spin-orbit coupling. You know, our electron is going to be trapped in a crystal, and it inherits some properties due to the crystal lattice. It knows that the lattice is there. And so there's a material-dependent and structure-dependent spin-orbit coupling that we can also look at when we examine spin physics. Okay? So the system that we're going to work with today is called a double quantum dot. And you can really think of this as a designer molecule in some sense. Here's a plot of the energy level of the system. And you know, physically, when I say double quantum dot, what I want you to think of is a double well potential that has one excess electron on it. And that electron can be in the left side of the double well potential, or we can tilt the double well potential and it can roll down into the right side, like in this picture, okay? So the Hamiltonian is just a simple 2x2 Hamiltonian. The energy of one state goes up with this parameter, so the detuning parameter. The energy of the other state goes down. And if these states are coupled together by tunnel coupling between the left dot and the right dot, there'll be hybridization of these charged states. So this gives you a standard kind of textbook two-level system of avoided crossing. Now, what's remarkable about these systems, Manda and I were in graduate school together, and I remember spending a lot of time trying to get metallic nanoparticles to gate or show any gate action. And semiconductors, I found as a postdoc, are much more forgiving, right? So everything in this Hamiltonian is gate voltage tunable, okay? We can push the electron from left to right by changing a gate voltage. You know, it's one knob. We can also adjust a gate on the device that tunes the barrier height that separates the left quantum dot from the right quantum dot, and we can tune this tunnel coupling parameter. And this can be done very rapidly, you know, on time scales that are a nanosecond or shorter. And so you can really drive coherent quantum evolution in the system and study it through time-dependent control of this Hamiltonian, okay? So this is kind of the starting point of our system. And let me describe how we actually make these devices now. So our nanowire devices allow us to make a double quantum dot. What we do is we take a single indium arsenide nanowire, and then we locally gate it and selectively deplete that nanowire to create this double well potential. Our nanowires are grown using an old process that was developed back in the 1960s, actually. It's called the vapor liquid solid growth process. And what we do is we start with a substrate, we deposit some gold catalyst particles on it, and we use metal organic chemical vapor deposition to grow a little forest of indium arsenide nanowires. These are about 50 nanometers in diameter. They're kind of quasi 1D structures, and they grow vertically. Here's a transmission electron microscope image of one, so you can kind of see what we're looking at. At the top of the wire, there's a gold particle. That's the catalyst that actually nucleates the growth. And so by setting the size of these gold particles, we can, with some degree of control, set the diameter of the nanowire. It's kind of a nice process that way. To make a device, we take one wire and lay it down on a substrate that's been patterned with gate electrodes. And the gate electrodes are running vertically in this image here. The gate electrodes are used to just selectively deplete regions of the nanowire. Okay? So it's N-type, and by putting negative voltages on these gates, we can create a tunable double well confinement potential. We can also perform standard transport measurements. And the way that we do this is by contacting the nanowire with drain and source electrodes. These are big ohmic contacts on the ends of the nanowire that allow us to get electrons in and out of the device. Yes?
Quick question. Did you say that the gates are already there and the wire is kept up top?
Yeah, that's right.
That's true for the source and the drain as well?
Source and drain goes down after everything. Yeah. We tried top gating, and I can tell you why, you know, later on it didn't work so well. But bottom gating works quite well. The E-beam tends to damage the wire. And so flipping the order was helpful. Okay. So this is what you should have in mind in terms of the confinement potential. We have a double well confinement potential, and it's tunable. And we can trap electrons in this double well confinement potential. To understand the transport properties, it's useful to look at a circuit diagram like this. So we have a left quantum dot, a right quantum dot. We can tune the local chemical potential with these gates, which have voltages V left and V right. And one important part about these devices, right, is they're very small. we're talking about a potential that is maybe 30 or 50 nanometers in diameter. And so if you calculate the capacitance of that, the capacitance of our dot is about 10 to the minus 18 farads. And that means that the charging energy, E squared over 2c, this can be 5 or 10 millielectron volts. This is substantial energy at low temperatures at least. And this charging energy leads to something that's called Coulomb Blockade. And so we're going to look at diagrams like this throughout the talk. This is called the charge stability diagram. And the numbers here denote the numbers of electrons trapped in the left and right side of the double well potential. So 0, 0 means nothing in the left dot, nothing in the right dot. And if we increase this right gate voltage and make it more positive, we can pull a single charge into the right quantum dot. That's a 0, 1 charge state. If we go up this way and make the left gate voltage more positive, we can pull a single electron into the left quantum dot. That's a 1, 0 charge state. So this is kind of a map. It shows if we put the voltages on these gates in a certain regime, this diagram tells us what the electronic occupancy is. Any questions about this?
What are the BL and DR gates?
These are the barrier gates. That's the left barrier, which tunes this barrier, this tunnel barrier. All right, so there's a big source and a big drain out here.
Okay, so you want to shield them.
That's right. This is kind of the shielding that isolates that molecule from the outside world. And then there's a middle gate which tunes this.
Middle one.
Yeah. Any other questions? Yes.
One would assume that the diameter of the rods is critical to your experimental diagram. So how do you select the diameter?
Of the nanowire?
Yeah.
We like to go as small as possible because we want to get down to 1 electron. But if you go too small, then disorder can become a problem. And at low temperatures, the wire, due to disorder, might unintentionally, form quantum dots in it. So we found empirically, through many measurements, that 50 or 60 nanometers works for us in terms of getting right-sized device. If the wire is too big, you'll have a hard time depleting it and actually, making quantum dots.
VLS often gives slightly tapering rods. Do you have any problem with that?
Well, you maybe can detect a tiny bit of tapering here. It's a little bit thicker at this end compared to the other end, but on the scale of our devices, it doesn't seem to have a big impact. If you really increase the growth temperature, then you get a lot of tapering, and that can be a problem. But under the right conditions, this is what the wires look like, and our dot diameter is 50 nanometers. So really, we're probing a region, somewhere. It's pretty small, right? Not very long along the length of it. One more question in the back.
How do you generate that stability diagram? What do you measure to generate that?
Yeah, let me show you. I'll show you how we measure this in a second. Okay. This is a sort of theory from electrostatic model, what you'd expect. The right dot has a charging energy, the left dot has a charging energy, and then actually there's a cross capacitance between these dots, which means that the energy of the left dot depends on how many electrons are in the right dot. That gives you this little splitting here. So that's the sort of physical picture for this diagram. And we can measure it a number of ways. Here's one. Here's a plot of the current in a color scale as a function of right gate voltage and left gate voltage. And I don't know if you can see this in the back, but there are pairs of points where we see current. And these pairs of points correspond to these so-called triple points where you can have resonant tunneling through the device. That's one way to probe it. And a few slides later, I'll show you how we can probe the stability diagram through a cavity measurement, which is actually, it gives you really what you're asking for. It just jumps right out at you. Yeah.
Quick thing. So, there's also a trick in realizing which box you are in, right? In terms
Yeah.
of- and that's just got to do with the relative sizes of the box, or?
So there's kind of a long history here, but what we do now, if we really want to know that we're at 1 electron and not 100 or 200, we go all the way to this corner until we see no more transitions. And you need to be careful when you do that to make sure that the tunnel rates to the outside world are still large enough. So there's a combination of kind of using transport and charge sensing to really lock those numbers down. But I'd say, 10 years ago, we weren't always super confident about the absolute occupancy. But now with the charge sensing, I think it's really nailed down. We'll also see shell filling in some cases. As you load electrons in, you expect sort of even odd loading. And you can see that in the addition energy. So there are a number of signatures that all kind of point in the same direction in these devices. These nanowire devices are harder to get down to 1 electron. So the experiments I'm talking about today, it's more like 10 or 20. But in our silicon devices now, we really work with 1 electron in each dot. Yeah? this diagonal section, it's set by this, basically it's a ratio of this mutual capacitance to some other capacitance in the system. It's a capacitance ratio. So it's this capacitance. If I take those dots and pull them apart infinitely, then there's not going to be any capacitive interaction, and that splitting goes away. Okay. All right, good. Let's talk about the cavity. So here's what the cavity looks like. You know, our standard picture of an optical cavity is two mirrors facing off against each other. VJ's group works with devices like this. These are called superconducting resonators. And the way I like to explain this, you know, is take a coax cable and cut it in half with a knife. And there's a center conductor in the coax cable, and there's ground plane on the outside of it. And to make a resonator, we're just going to cut that central conductor and have a length lambda over 2 so that we can set up electric field with this kind of profile. So the superconducting resonator is pretty simple to make lithographically. It's pretty large. The scale bar here is a millimeter, so this chip's about a centimeter across. And we can have quality factors, you know, in the range of a few thousand for our devices, kind of typically. Let's talk about, you know, how a real sample looks. This is a device that we measured a few years ago now. The scale bar here is a millimeter, and length of this sets the resonant frequency more or less. Okay, and now we're going to zoom in. This is a optical micrograph with a 10 micron scale bar, and what you're looking at, this is the center conductor of the superconducting cavity. And now I'm going to zoom in again, this time with a scanning electron microscope. Now we're down to about 100 nanometer scale bar. And at this scale, you can see an individual nanowire with the bottom gates underneath it. And we're doing a couple of things here that are somewhat different from the superconducting qubit type experiments. We have a really small device that we want to couple to the cavity field. And to have a strong electric dipole interaction, we actually lithographically connect the source contact of the nanowire to the cavity resonator. And we connect the other half of the device to the ground plane. And so the voltage across this superconducting circuit is getting dropped across about a half a micron, the gap between these source and drain electrodes. And that gives us a large electric field in the region where the quantum dot is living. Okay?
It's the source plane.
Yeah.
Cavity field is driving the source plane.
That's right. Yeah. It's sort of a differential bias. We also do this now in more recent experiments with a gate coupling. It's very comparable in terms of the overall G's that we get out. Another thing that we can do with this system, there's a little, you can't really resolve it in the back of the room, but there's a spiral inductor here that acts as a low-pass filter. And we can apply a voltage to this and basically bias a DC source drain bias across the nanowire and measure the current through it. So you can do standard DC transport measurements and microwave frequency measurements through this device. Okay, so the gentleman in the back asked, how can you measure the charge stability diagram? So what these data show is actually the microwave frequency phase response of the cavity, okay? So I should talk about how we measure the microwave response. We shine microwaves in the cavity, and we look at what comes out the other side. And so you shine light in, light comes out the other side. You can look at the amplitude response, the amplitude out compared to the amplitude in, and also the phase response of that field. So what's plotted here is the phase response as a function of right gate voltage and left gate voltage. And we're zoomed in here, but these are basically, this is a charge stability diagram, okay? I don't have time in this talk to describe every feature in this plot. So I want to focus on this red line that's running diagonally here. This is a so-called interdot charge transition. And an interdot charge transition is a charge transition that conserves total electron number. So it basically just corresponds to tilting the double well potential one way or the other, but keeping the total number of electrons fixed, okay? Up here, where the white dot is, the electron is in the left side of this double well potential. Far over here, the electron would be in the right side of the double well potential. We've tilted it. And right at this transition, the left dot charge state and right dot charge state are resonant. Okay, so they're hybridized by the interdot tunnel coupling. And so one question you might have is, right, this is a centimeter sized cavity, and the double dot's only 100 nanometers or so in size. It's not obvious that this huge cavity should care at all about this very small quantum dot system, right? And so the physics here is, here's again the double quantum dot energy level diagram. And the way you can think about this is this cavity is generating, when it's driven, it's generating a small oscillating electric field. And that electric field couples to the double quantum dot energy levels and causes them to oscillate. If the levels are far attuned, that oscillation doesn't do anything because it doesn't have a large enough amplitude to cause an electron to flop from one side of the device to the other. So up here, there's no cavity response because there's a very large energy detuning. Down here, there's no cavity response because there's a very large energy detuning. But right at this inner dot charge transition, we've brought the left and right dot states into resonance, and a very small excursion in gate voltage can cause an electron to flop back and forth between the dots. And this gives us a large shift in the cavity phase response. And so that's a way of thinking about this level diagram is take the second derivative and think about the curvature of these bands, and that's the susceptibility, the charge susceptibility or polarizability of our system is maximum right here at the zero detuning. That's why we have a strong phase response there. We can look deeper into the physics here and actually measure the charge cavity coupling rate. In our device, that's about 30 megahertz. Okay, so that's the electric dipole interaction strength between one electron in that device and the cavity field, just to give you an idea of scale. Okay? All right, so that's just the background of how the device works, how the cavity works. Let's talk about the non-equilibrium physics part now, is how can we actually make this laze? So what we're going to do is we're going to take the double dot and we're going to hook it up to a battery. And a nice way to think about the double dot physics is to plot the charge stability diagram now, but to think about the case of finite bias, where we've hooked the source and drain electrodes up to a battery. That opens up a bias window, energy range over which electron transport's allowed. So we can have an electron hop into this level, hop to the left level, and come out the other side. And this transport is only allowed within these triangular shaded regions. These are called finite bias triangles. If we go outside of the triangle, in one direction, it would be equivalent to pulling these levels down. And then these levels would be below this Fermi sea, and I couldn't get the electron out. We could also raise these levels up, and there'd be no way to get an electron on the dot, so the current turns off. So there's a very strict set of conditions that need to be obeyed to have current flow, and you only get current flow within these finite bias triangles. Okay? So that's some more double dot mesoscopic physics in terms of the device. Another thing that's useful to think about, we generally think about large macroscopic current flows, amps, microamps. This is really a single electron transport cycle, and you can think of it in terms of the electron number changing. For example, I can start with an empty double dot, add an electron to the right dot, kick it over to the left dot, and push it back out the other side. And it's really the electron occupation in the system that's changing according to the cycle here. All right, so this is a cycle that moves one electron through every time you kind of go around in this charge stability diagram. Okay? This is what we expect from theory. And so now we can measure this. This is current as a function of the gate voltages. And what you can see here, I've kind of marked it to make it clear. There are triangular regions where there's non-zero current. These are the finite bias triangles that we expect from theory. Now, what we found intriguing at the time is we could also look at the transmission through the cavity as a function of these gate voltages. And in past experiments at zero bias, we always found that the double dot just damped the cavity. It made it worse. It made the quality factor lower. But we found when we applied a finite bias across the device, there are actually regions close to this interdot charge transition where we saw gain or amplification. And the amount of gain here is rather modest. It's maybe 20%. But what these data say is that we have a current flowing through the device. We're shining light into the cavity, and somehow we're getting more out of the other side of the cavity than we're putting in. And this double quantum dot's acting like an amplifier in some sense. And the physics of this is early theory from 2011, that's pretty close to being correct, is that the application of the source drain bias continually repopulates the excited energy state in the double quantum dot, and it kicks you back up to the excited state, where you then have population inversion and you can have stimulated emission. And so it's really this single electron tunneling cycle followed by these stimulated emission events that gives us gain in this device, or could give us gain. That's the rough picture of what's happening here.
In the current that you measure, things are a bit fuzzy, and you see some current even outside the two triangles. Is it because of co-tunneling or?
Yeah, this is a co-tunneling here, and I'll show you, I think there's some more data on the next slide where we've opened the device up even more and there's even more co-tunneling. But generally, to see this gain effect, we need to have a fairly high current. It's about a nanoamp, and most of our qubit experiments would be about a picoamp kind of current level. So the rates to the leads are pretty high.
And the cavity should make sense. The cavity is insensitive to co-tunneling events.
Yeah, we haven't seen any strong signatures of co-tunneling, virtual tunneling events. Yeah. Okay. So this shows that we have gain or some amplification from these tunneling events. And then this is even less pretty data. But the main thing to point out, the current's 10 times higher. So we made the barriers more transparent so that we can get a higher current flow through it. And in this experiment, we can actually just take a spectrum analyzer and listen to the device, measure the power spectral density of the radiation coming out, and we see that the device acts like a photon emitter. And so the photon emission rate is about 10 megahertz within our measurement bandwidth, above the background noise of our amplifier. This is a standard HEMT amplifier. Okay? So we see photo emission from the device. Another thing that's interesting is if you measure the transmission, you see these gain features. At the gain features, there's actually a pretty dramatic narrowing of the cavity resonance. And so this is the transmission through the cavity in Coulomb Blockade. It has a quality factor of about 3,600. But if we go to a spot where we have a large current flow and we have gain, we see gain of about 10 in this case, but there's also a pretty dramatic narrowing of the cavity line width. So this is starting to smell like a laser maser. So we looked at the numbers, we started to think about the physics of our device, and this comes back to your question earlier, so what are the overall rates? But there's a parameter called cooperativity, and a way to think about the cooperativity physically, it's sort of the ratio of the good couplings in our device to the bad couplings. The good coupling is the vacuum Rabi coupling. It's the electric dipole coupling that couples that charge, the electric field. The bad coupling, unfortunately, has two different types. There's a photon loss rate, kappa, because our mirrors aren't perfect in the cavity, and our qubit is not perfect. So there's a qubit decay rate, gamma, and we'd like this cooperativity to basically be greater than 1. And so if we plug in parameters for our device, our cooperativity is about 0.6 roughly. It's less than 1. So we started to think about this advice, anything will laze if you hit it hard enough, and what we could do to increase the cooperativity. You can make G larger, or you can make these decoherence rates smaller, or you can kind of do a brute force experiment. And we just decided to do the brute force experiment. This is my graduate student, Yin. She's really great, push these experiments forward. She made a device that we call a double-double. And the double-double is basically our old device, but now we put 2 emitters in it. So instead of having one double quantum dot, we now have 2 double quantum dots. One's at the left end of the cavity, one's at the right end of the cavity. And that basically doubles the pumping rate, doubles the gain rate of our system. We were hoping that this would push us across the cooperativity equals 1 threshold. Okay? So here's the picture I have in mind for this experiment. It's the same microwave cavity more or less, but now we have 2 double dots, and each one is independently tunable. We can turn them on and off as desired. Now what we can do is we can measure the power gain. This is the ratio of the output power to the input power as a function of frequency. And remember, we can voltage tune these devices. We can turn them on and off. If the current is 0 for both of these devices, then there's no gain, and we see a kind of boring Lorentzian transmission. If we turn one device on so that there's a current flowing through it, we see gain that's about a factor of 10 in power. And what was pretty surprising is if we turned them both on so that there was a current flowing through both of these double quantum dots at the same time, then the gain just exploded, and we had a power gain of about a factor of 1,000. And really, dramatic narrowing of the emission line width. And so this, yep.
Was there an asymmetry between one of the conductors on? You have one on, it's the green and the blue are different.
Yeah, you're asking about the difference. Yeah, these are fabricated devices, and the coupling is always a little different. The decoherence rates are always a little different. So there's some tunability in terms of this. And maybe you can see that from these data. We were able to change the current from 10 nanoamps. For, previous slide, it was like 10 picoamps here. So you can tune things, right, to set up the potential. And it's difficult to get them exactly the same. Yeah.
So both the double quantum dots are biased at the same point of the phase diagram in this, so they're shuttling the charges.
Yeah, the way I would think about this is there's a stability diagram for the left double dot and a stability diagram for the right double dot, and we've parked both of those on the kind of maximum gain feature, in this 2D plot. So does that make sense? Yeah.
These are independent quantum dots, right?
Independent.
Even the source drain current is not in series, is it?
It's in parallel. The source drain is the only thing that's in parallel because we only have one bias point on the cavity. So the source drain biases are the same, but the level detunings and positions we can do whatever we want with, with the gates.
I shouldn't really be thinking about interaction between these two dots. Right? They are two independent emitters, but they're emitting into the same resonance.
Right, that's right. The same reservoir. It's really like the cartoon. It's like, Is that a quick question?
How do you estimate the number of electrons? Is it from the current which is passing through?
The total number of electrons in the double dot, we can make a rough estimate from the charging energy. How?
Your current is varying from picoamps to nanoamps. If it is single electron, we expect around picoamps of that.
Well, the current rate depends on the height of the tunnel barriers. And that can be tuned in a number of different ways. So you want to look at both electron number, kind of the size of the dot, as well as the size of the barrier between the dot and the outside world. And in a device that's designed well, they're not 100% decoupled from each other, but you can control dot size, electron number, and the tunnel rates kind of, somewhat independently. Yeah, that's kind of a detail. Yeah.
Regarding the previous question, what is the reason why the two quantum dots does not have interaction? Is it with the losses?
Well, in this particular system, the charge dephasing rates are really high in our nanowires, or a few gigahertz. And so, this is incoherent. Don't think of any, like charge Rabi oscillations in the double dot. We're sort of out of that regime. We're not in strong coupling in this device. Yeah. Okay. Another thing that we can do is we can measure the power spectral density emitted by the device as a function of frequency and extract a line width of this maser. It's about 34 kilohertz. That corresponds to about a 10 microsecond coherence time or a few kilometer coherence length. So that's how the maser operates. And then another thing that we can do is compare with what's called the shallow Towns limit. A shallow Towns theory gives a prediction for the minimum line width you'd expect to have for a laser. And it's kind of a good benchmark to compare your system with, this theoretical upper limit. And the basic idea is that, in a maser or laser, there's a competition between stimulated emission events that add up coherently and random spontaneous emission events that every now and then kick this phaser around and randomize its phase and amplitude. And so you can see from this plot, if we can increase the overall intensity of the field in the cavity, then we're going to be less sensitive to these random spontaneous emission events that come along every now and then. And so there's a nice simple prediction for the minimum line width of a laser based on basic properties of it. And for our system, we expect a line width, it's about 400 hertz, and our line was significantly broader than this, about a factor of 100 bigger than the prediction. And the reason is that you asked about coherent interactions, right? These energy levels are sensitive to fluctuations in the device, right? They're gate voltage tunable, and so the level detuning is actually kind of inhomogeneously broadened, if you want to think of it that way. The energy levels are shaking around as a function of time, and that actually impacts the maser properties. Okay, so the kind of real smoking gun.
Sorry.
Yep.
What exactly is the shape of the spectrum?
Our spectrums are Lorentzian.
That is using a fit and
Yeah.
finding the chi-square? That's the best fit of the spectrum?
Yeah.
Then what is called inhomogeneous?
Oh, I can show you some data later on. We've done some more sophisticated analysis. I'll kind of get to it to look at the statistics in more detail. And so we can actually measure sort of histograms of the output field as a function of time. in time series of the actual output field and look at the fluctuations in that.
I was just related to inhomogeneous bonding with your Gaussian shape.
Yeah, just an analogy in terms of energy levels. You know, we typically think of a detuning parameter as being fixed, but ours isn't. I mean, in our system, we have 1 over F noise that causes the levels to shake. And that couples to the gain, you know, in a non-trivial way. So the inhomogeneous broadening of the transition doesn't mean that that line width is exactly sort of following that. You know, there's a complicated set of equations that links the two. Yeah. But actually what we see is there are extreme cases where the level detuning shifts and the laser blinks off, you know, turns off. And we can see this in time series. So we're pretty confident that it's 1 over F noise and charge fluctuations. Okay, so what we want to do is actually verify that this is a coherent source. And a nice way to do this is to measure the statistics of the emitted radiation. And here's a nice picture to have in mind. This is from Siegmund's great book on lasers. But imagine, you know, thinking of the electromagnetic field of this device in terms of a phasor diagram. And if we had a thermal source, the magnitude and phase angle of that emitted field would just randomly vary as a function of time, you know, centering around 0. And this is what a thermal source would look like. If we have a stable oscillator, it's going to have a fixed amplitude, ideally, or small fluctuations in the amplitude, and it's going to coherently process around, you know, in a complex plane at a frequency set by the field, right? So you'd expect to see a very different type of histogram. And so we set out to measure this, and it turns out this is actually quite hard and complicated. And, you know, the reason is that if you work with an optical system where the photon energies are electron volt, you can just buy off-the-shelf single particle, you know, single photon detectors and measure clicks and coincidence counts and extract all these correlation functions. But our dots are big, the energy levels are small, and the photon energy is about 30 microelectron volts, right? Which is much less than KT. So you can't use standard room temperature amplifiers. So we spent a lot of time, you know, reading papers by other groups in the field and started using parametric amplifiers to actually measure these photon statistics. Okay, and so with that, we can measure the statistics of the output field. This is what the histogram looks like. And let me explain these data. This device is emitting electromagnetic field. We sample that for about a second, and for each microsecond of that 1 second interval, we extract an amplitude and a phase, right? And we make a histogram of those 1 million measurements, and that's plotted here, okay? So this is what's shown below threshold. It looks thermal. If we turn a current on through both of the devices, then it takes on a very different qualitative shape, right? It has a ring type shape. We also see that the amplitude of the field is about 10 times bigger. The scale here is 100, the scale there is 10. So there's a big increase in the output field, and we also see this ring type shape. Now this is broader than expected based on a coherent source significantly, and so there are other things that we could talk about in more detail in terms of the fluctuations. Okay. But this shows that we made a coherent oscillator that's driven by these single electron tunneling events. About out of time, I just want to explain this experiment quickly, the single electron Sisyphus effect. So what I showed you so far is that we can hook this device up to a battery, and that forces electrons to tunnel through sequentially. But you can also do these experiments in a more controlled manner and basically decouple that double up potential from the outside world, put 1 electron in it, and then apply a time-dependent perturbation to the double quantum dot energy levels. And this is kind of a more recent story I want to talk about. But here's the rough picture we had in mind, you know, initially when we started off thinking about this experiment. Let's take 1 electron and put it in the double quantum dot. At low temperatures, it's going to thermalize to the ground state. And now let's apply a non-adiabatic voltage pulse to this device, which drives the electron up into this excited state, where it then decays. And the idea was to make basically a single photon source. Push the electron up, it decays by emitting a photon, and you can do this 1 electron, 1 photon at a time and kind of have a turnstile. So our naive picture was just kick this electron back and forth with non-adiabatic pulses to try to make a microwave frequency photon source. And what we found was actually much more complicated, you know, and beautiful compared to the simple picture. This is a plot of the intracavity photon number as a function of the amplitude of that AC drive and as a function of the level detuning. And we see a complicated interference pattern. And this is actually one signature that shows that there's some coherence in this device, charge coherence in this device, is that we see coherent oscillations. For particular parameters of the AC drive amplitude, we see gain. That means we have stimulated emission. But for other conditions of the drive parameter, there's no gain. And the kind of picture to have in mind is, as we sweep back and forth, you can think of this as an interferometer. So it makes Landau-Zener interference. We're actually accumulating phase as a function of time, between these two energy levels. And for specific parameters, the phase can add up constructively, and for slightly different parameters, it can add up destructively, right? So depending on where you sit and how fast you sweep, you can generate this interference pattern. Now, what's kind of neat about this is we can measure the current through the device as we do this pumping, and that's shown in green. This is the current through the device in green, in units of picoamps. And to within our noise, it's 0. And these data really show that by taking one electron and pushing it uphill and having it decay and pushing it back uphill, you can actually make light. So one electron produces many photons through this process of the non-adiabatic driving. And so this is also a kind of interesting story that we've been looking at with these devices. Yeah?
So if they're interfering, it means that your decay rates are not strong enough, right? Essentially, it's not, every once in a while it's not decaying, so when you go back, and that's what the coherence builds up and integrates, but that would just be a question of the different parameters you choose. I mean, do you want this interference if you want to make a single photon emitter, or you really don't want this interference to happen? I mean, ideally you would like the photon to be emitted every time you go back.
Yeah, that's right. And there's another more complicated part of the story is that there's electric dipole coupling to the cavity, but there's also strong electron-phonon coupling. And so we can have transitions from excited state to ground state that don't generate light, they just generate a phonon and lattice vibration. And to analyze these data and kind of come up with this fan diagram that reproduces the experimentally measured one, you need to take these phonon events into account. So it's kind of a competition between phonon loss and photon loss. And yes, if you want to make a turnstile, you'd like to get exactly 1 photon out per cycle, but we don't. We have to do about 1,000 cycles to get 1 photon out because the direct phonon matrix element's quite a bit bigger. Yeah.
And these are all stimulated emission events? There's always a tone, or there's no tone?
This is no drive in this case. So we have a couple of different measurements kind of shown in this paper, but you can actually just listen without a drive. You can drive it as well with a small tone, and you see the same interference pattern more or less. But you can get light out without any internal drive. Yeah. But it's not extremely efficient though. And also we can go through the quantitative analysis of our maser at finite bias, and the efficiency is about the same. It's like every 1,000 tunneling events you get a photon out roughly. Okay. All right, so let me wrap up with this. I just want to highlight one more recent result before I finish. And there's been an issue with the indium arsenide devices. There's a lot of surface area on the nanowire, and there's a lot of dirt stuck to the surface of the nanowire that leads to this inhomogeneous broadening of the quantum dot energy levels. And so more recently, we started making devices in silicon, quantum well structures, and the charge noise is much smaller. We have line widths now that are a few megahertz, where we used to have gigahertz line widths, and it was possible to reach a strong coupling. But now with our silicon devices, we can reach the strong coupling regime and actually resolve vacuum Rabi splitting in a semiconductor double quantum dot device. And so we're in the process now of doing time domain experiments. Another thing, thinking in terms of the future, there's this beautiful work by Capasso and others, Claire Gamakel, on quantum cascade lasers and quantum well systems. And we started thinking, we've made a device that operates by single electron current flow. Maybe we can make a quantized version of the quantum cascade laser where you have a mini dot system, say 5 dots in series, and a cascaded event of photon emission events. And so this is something that we're also thinking about looking into in terms of generating interesting states of light. So with that, let me just summarize. I hope I taught you a bit about double quantum dots, and I hope you have a good qualitative understanding of how these devices work. Showed you that we can make a maser by driving a current through a cavity coupled double dot. We can look at the photon statistics, and that confirms that this is a above threshold maser. You can also look at non-equilibrium physics that's driven by pulsing these quantum dot energy levels in a non-adiabatic fashion. And so this is another way to generate light using single electrons. And with that, I'd just like to thank my group for all of their hard work, and thank you for your attention. We're always looking for good people, good students, and so if you like this kind of physics, send me an email. Thank you.
More time for questions.
So how are you putting all these quantum dots exactly in those positions? So how do you plan to?
How do we kind of make the device? There's a little bit of magic. I don't do the work, the students do, of course. Let me go back to this slide. Right, so there are a couple of things here that I think alleviate a little bit of the pain compared to an atomic physics experiment where you have two mirrors and you really need to make everything small. I mean, this cavity is pretty big, it's about 1 centimeter, and that's set by the wavelength of the radiation. And so you just need to get the nanowire someplace where the electric field is close to an antinode in the cavity where you have a large field. And so if the centimeter scale device that's not that small really, you can do this. And so the way that we do this, we have two approaches. One is just to randomly disperse nanowires like has been done with carbon nanotubes and other things. And that's how these devices were made. More recently, we built a little micro-manipulator stage, and we can pick up a single wire from the gross substrate and then move it over to a chip like this. And the really good students can land it within 5 or 10 microns of where they want it to go. Okay. All right. So with a little bit of work and magic, that's how it's done. This isn't a process. Nanowires are good for kind of one-off, physics experiments, but it's very difficult to make many, many devices that are all identical. This is good for exploratory work. The silicon devices that we make now, it's very different. I mean, we can make many, and they're very similar in terms of properties. Did you have a question, Vijay?
Yeah, so going back to this part where you discussed cooperativity,
Yeah.
it's just below 0.6. But one of the parameters where just easily control is kappa
Mm-hmm.
of this microwave resonator.
Yeah.
So was there anything particular why putting 2 quantum dots was easier than just dropping kappa by a factor of 10?
Yeah, I'd say that, so the question is, you have the good coupling, which is a vacuum rocket frequency. You have bad coupling, which is your qubit's not perfect, and it decays with some rate that's hard to change. You have a cavity that, in theory, you can change the reflectivity of the mirrors to change the cavity decay rate. We actually have some problems due to internal losses with our cavity. And I'd be happy to hear your advice on this if you have ideas, but we need to get a DC bias in. And so we have this inductor. We also have all these gate lines that are going into the cavity. And the gate lines are really nice paths for microwaves to leak out of the cavity. So it's not so much that the kappa in and kappa out are the problem, it's that our kappa internal really sets the overall kappa. Yeah.
So that's only can be a megahertz or so? All these leakages?
What we've done more recently is we started adding LC filters to these gate lines, low pass filters, so that we can get DC in, but so that the transmission is small at 8 gigahertz, and that's helped a lot. But there's still some materials physics here. You have in this system there are wires and gates close to the device. In our silicon samples where we have strong coupling, the Qs are better, they're about 8,000, but they're still not 50,000 or 100,000. We'd like to get them there. But there's a quantum well that you need to do your fabrication on, and that quantum well can only withstand so much abuse. So in terms of cleaning and other things, we could be, 2-level system dominated in a certain regime as well.
For
So
the indium arsenide devices, the substrate is what?
these experiments were just oxidized silicon that we did the niobium deposition on and fabrication on.
Intrinsic silicon?
Yeah. A sort of float zone, high resistivity silicon. So in principle, we've made bare resonators with good Qs. on silicon, but once you start adding all the associated gate lines, you know, the resonator is now chopped up into many different pieces, and I think some of it's microwave engineering as well. So we're looking at flip chip now, where the cavity is going to be fabricated on one chip and the quantum dots on a separate chip, and you kind of bond those together. And I think that will alleviate some of the constraints. Any other questions?
Yes, it should be, leaving aside the gain part, it should be easy to map the chains coming laterally in the system, right?
If in the strong coupling device, yeah. And these devices are just, the nanowire devices have been way too noisy to really look at James Cumming physics in too much detail. Yeah, but now with our silicon devices, the noise is down into the few megahertz regime, and we have good, you know, strong coupling. And yeah, we're digging into that physics more now.
Do you imagine measuring the vacuum speed?
Yeah.
I had a question. In your in these experiments, would there be some interesting physics if you have the gaps due to the electrodes open up, like, you know, essentially the tunneling also governed by the superconducting gap of the source drain?
Okay, so instead of, you know, using Thai gold for contacts,
Yeah.
contacted to superconducting contacts, I think Takis is going to be here in a few days. You know, he's made some nanotube devices that they can be proximatized pretty easily, and they've looked at what happens in the superconducting regime, and, you know, due to this strongly peaked BCS density of states, you can see some lead photon emission from dot lead tunneling events. It's a little bit hard to understand where the dipole moment comes from in that kind of picture, because you're coupled between a discrete level and a continuum. Whereas for the double dot, it's, you know, two discrete levels, and there's a nice theoretical picture. But they have seen some evidence of coupling in the cavity measurements in those systems. But yes, I agree, that'd be another interesting thing to look at.
Okay, if there are no more questions, it's time for a fascinating.
Thank you.